For our next assignment, we're going to jump over to section 4.8. We're going to skip 4.7. So section 4.8 is about graphs and derivatives of implicit relations. And your essential question is, how do you find the derivative of an implicit relation and show by graph the answer is reasonable? So we're going to start off by differentiating between explicit and implicit relations. So explicit relations we're really used to working with. I'm going to use relation and function interchangeably here, realizing that a relation may not necessarily be a function, right? You could potentially have more than one output for every single input. All right, so an explicit relation is explicitly stated y as a function of x, or a relation of x, okay? So in this case, y would be your output, x would be your input. Okay, and this is what we're really used to working with, right? Is functions that have an input of x and an output of y. Okay, so an example of that might be something like y equals x cubed plus 3. Okay, now sometimes though, it's not explicitly stated that y is going to be a function of x, or that y is necessarily your output. So an implicit relation is that kind of a case. This is where it's implied that y is going to be your output. Implied that y is a function of x. So an example of that might look like x squared times y plus y squared equals 25. Well, we can always take functions or relations and we can solve them for y. However, in this case, there would be no way that I could actually solve for y. I could factor out one y and then divide everything else to the other side, but I'd still have a y being divided out. So I'm never going to be able to solve this just for y. So this is when it's, it's something where it's impossible to solve for y. Even though really y is your output and x is your input. So what do we do with something like this if we want to take the derivative? Right? Something like this is really easy to take the derivative with respect to x. Something like this is going to be very challenging to take the derivative with respect to x. So what we're going to do is we're going to do a thing called implicit differentiation, which we've already looked at when we were working with the inverse trig function. Sorry, that was getting away from me. So let's talk about implicit differentiation again. So there's really just 3 steps when you work with implicit differentiation, okay? The first step is to find the derivative of both sides of the equation. And you're going to find it with respect to whatever your input is. So like in this situation, we'd find the derivative with respect to x. Our next step is to express the derivative of the dependent variable And it really depends on what you're going to use. So in the cases above, I would say, I want the derivative of y with respect to x. But maybe you're talking about time. So maybe you want the derivative of time with respect to x. Or maybe you want, how about the derivative of the height with respect to time? Right? It really depends on what variables you're working with, okay? For right now, we'll just keep working with dy dx, but in our next lesson, we'll get crazy and we'll start working with all different kinds of variables. So when we're doing step 2 here, really what we're doing is we are doing the chain rule. Okay, so that's really what this amounts to. So for example, if I'm taking the derivative of y, well, taking the derivative of y, really, if I'm taking it with respect to x, is really a dy dx. Okay, and I'll show you what that is as we get into the next example. All right, and then your last thing is to solve for your derivative. So you're going to solve for dy dx or dt dx, etc. Okay, you're going to solve for whatever it is that you're looking for, the derivative of whichever variable, whatever your output is. Okay, so let's do an example. And I'm going to flip over because my example is going to be quite lengthy. So example 1, we're going to find the derivative. Let's see, we'll do a 2xy plus y squared, and that's going to equal 3. Okay, so I'm going to follow my rules here. So I noticed that, for example, I've got y here and y squared. There's not going to be any way here that I can solve for y. So that means that if I want to take the derivative of this, I need to do it implicitly. Okay, so using implicit differentiation. So step 1, find the derivative of both sides of the equation. Okay, so that's what I'm going to do. So I'm going to take the derivative with respect to x of this left side, and I'll do the same thing on the right side, the derivative with respect to x of that right side. Okay, so starting with this first term, well, I notice with this first term I've got a coefficient, and then I've got the product of two different variables. So I'm going to leave the coefficient alone, as we normally do anytime I have a coefficient, and then I'm going to have to do the product rule on x times y. So I'll pull the 2 out just like I would with any other coefficient, and now I'm going to do the derivative of this product. Okay, so the derivative of the first, which is the derivative of x with respect to x, which is really just 1, times the second, which is times y, plus the first, which is x, now times the derivative of y. Now this is one of those times where you think about yourself doing the derivative of y with respect to x. Well, that's really just dy dx, derivative of y with respect to x. Okay, now in addition to that, let's see, let's close the brackets because I took care of that first term. Now the second term, well, that's y squared. So now I'm taking the derivative of y squared with respect to x. So you start off with the power rule. Okay, so that's going to be 2y. And now I need to chain rule it. So that's that second step here, where you're going to express the derivative of the dependent variable using one of these things, or chain ruling. Really, so the derivative of my inside function, which is just y, is again going to be that dy dx. And then on the other side of the equation, taking the derivative, the derivative of a constant just gives me 0. Now I'm going to use the distributive property to simplify this and get rid of these brackets here. So I'll have 2y plus 2x dy dx plus 2y dy dx equals 0. So now I'm at the point where I need to solve, or I need to follow step 3. And that's where I'm going to solve for my dy dx. Which means I need to get dy dx all by itself on one side. So first of all, I see that out of my 3 terms, I have 2 of those terms with a dy dx. So I'm going to get rid of that third term that does not have a dy dx, put that on the other side. And the best way to solve for something, if it's in both of your terms, is to factor it out. So I'll factor out a dy dx, and then I'll be left with the 2x plus the 2y equals negative 2y. Okay, so getting dy dx by itself, I'm going to have to divide both sides by 2x plus 2y. Okay, so these go away. So I'm left with dy dx equals negative 2y. And I'm seeing that I'm probably going to be able to reduce out a 2, so I'm going to factor out a 2 in the denominator. Okay, so the 2's reduce, and really the derivative of y with respect to x will be negative y over x plus y. Okay, now we're going to do an example out of the book. We're going to look at page 170, and this is the example that's on that page. So we are going to consider the implicit relation x squared plus y squared equals 25. And if you don't remember, this is the equation of a circle where it's always equal to the radius squared. So that means that the radius here is 5. So if you look at the circle in the graph, you'll notice that, well, at least on my axes, from the origin, I'm 5 spaces. Now, how could I figure out if this entire thing is 5, if every single point on this circle is 5 spaces from the center? I can always use Pythagorean Theorem, right? So if I needed to know the hypotenuse here, then maybe I would know the height, okay, and then this leg, and then I could find that hypotenuse. But I already know that this is a circle because every single point on this circle is the same exact distance from the center of the circle, which happens to be the radius, which is 5. Okay, so I've already explained why the graph is a circle. Okay, now let's get into the harder stuff. So we're going to differentiate implicitly to find dy dx. We're going to calculate 2 values of y when x equals 3. And then we're going to draw a line with slope dy dx through the point found in part C with the lower value of y. So we're going to find 2 values here, and then we're going to take the lower value. And how is this line related to the graph? Alrighty. So starting out with writing the equation is x squared plus y squared equals 25. And I'll go ahead and I'll draw myself a picture. A rough estimate. And we know that if it's a circle, every point on the circle needs to be equidistant from the center, although mine doesn't really look that way. But pretend like it does. Alright, so I'm not going to explain A. I already have done that. Let's go ahead and go into B. So we're going to differentiate implicitly. Okay, so that means I'm going to take the derivative of both sides here. Okay, so I'm going to take the derivative with respect to x of this whole thing, and then I'll do the same thing on the right-hand side with respect to x. This one's a little bit easier than our last one. So taking the derivative of x squared, well, that's going to be 2x. And I know it doesn't seem like it, like we don't usually use the chain rule when we're taking the derivative of x with respect to x, but really we are. So I can use the power rule here and get 2x, And then if I think about taking the derivative of the inside function, well, that would be the derivative of x with respect to x, or dx over dx, which is actually 1. Okay, so even though we don't think about it, we're actually doing that. Okay, so I'm done with the first term. Now my second term, I'll do the exact same thing. I'm going to do the power rule, so bring down the 2. I've got 2y. And then I need to do the chain rule, so the derivative of y with respect to x. And on the left side, or on the right-hand side, derivative of any constant is going to be 0. So now I need to get dy dx by itself. So I'm going to have to subtract that 2x and then divide by 2y. Which then really just simplifies to negative x over y. Okay, so we found the derivative of y with respect to x. All right, so for C, we have to calculate the two values of y when x equals 3. Okay, so if you think about this graph, there are two values for every, that's why this isn't actually a function, right? It's a relation. So when I put in x equals 3, I get out two things. I get out a positive 4 and a negative 4. So let's actually calculate that algebraically. So going back to my original function, I'm going to have x squared plus y squared equals 25. So when x equals 3, I'll just plug 3 in. So I'll get y squared equals, and that's a 9. I'm going to minus that, so I get 16. Taking the square root, then y is going to give me positive or negative 4. Okay, so on D, it asks you to draw a line with slope dy dx through the point found in part C with the lower value of y. So the lower value of y is going to be the negative 4. Okay, so for D, we're actually going to use the point 3, negative 4. Well, at this point, dy dx, or the slope of the tangent line, is going to be negative 3 over negative 4. All I've done is I've just plugged these points into my derivative, or in other words, 3/4. Okay, so that's my slope. And so now I'm going to actually draw that line. So it's going to be a rough drawing, but I'll attempt to make this look like a circle, even though it's really hard without graph paper. Okay, so there's my rough circle. I'm just going to go to the point 3, negative 4. And I'm going to draw myself a tangent line. And that tangent line, I'm going to show it as having the slope that I want, which is a rise of 3 and a run of 4. Okay, and I can say the line tangent to the circle at 3, negative 4 has a slope of 3/4, which equals dy dx. So something like that as kind of an explanation. So I drew it. Well, first of all, I calculated what the actual slope would be at that point, using the fact that I knew what the derivative was. Then I drew a really, really rough graph of that, but really showing that I understood that my rise would be 3, my run would be 4, and it would be tangent to the circle at the point 3, -4. And then I gave a nice explanation.